Hey PChem, as promised, want to produce a couple videos for you answering some questions I think you should know how to do. The first two in this clip will do weak acid dissociations and going through the math and seeing if we could come out with any interesting conclusions once we see our answers. In number 19, we've got a pretty nasty chemical, by the way, hydrofluoric acid, in two different concentrations. Let's see what happens in an ICE table when we go through the process. So I've got the dissociation here of the weak acid. Notice that I put in water. I notice that the textbook, Dr. Chang, does not. It really doesn't matter. We take our initial concentration of the 0.50 molar, and we assume that a little bit of it is going to dissociate with the equilibrium there with the given Ka. And for every one molecule which dissociates, we're going to get two pieces. We're going to get a proton plus X, and we're going to get a fluoride ion plus X. The new concentration of the hydrofluoric acid is 0.50 minus the little bit that dissociated. You could see that by placing this in the Ka expression of products over reactants we should, it looks like, have to solve a quadratic. But as I taught you in class, I think it's somewhat useful to know the method of successive approximations. That's where you take the value that you solve for, assuming that the x is small, and then rearranging the equation, keeping that assumption in mind. Whoops, made a little mistake there with the dot. Don't want that. 7.1 times 10 to the minus 4. And solving for x, I get 0.0188 for a concentration of the H3O plus and the concentration of the fluoride. That's what our x is. Was that a good approximation? Well, we have to do a little calculation. We need to take the x, and we need to see if it was less than 5% of the number that it was being subtracted from. I think it's clear here for you that it certainly is. This ends up being 0.038 or equivalent to 3.8%. So that's a good assumption. Okay. Do we find anything interesting if the concentration is changed to be 10 times more dilute? And so a lot of this is going to be repeated from what I did above. You start with your ICE table and the initial concentration of the acid. A little bit of it dissociates, and we're going to create a little bit of protons and a little bit of fluoride ions. You might recall that there's an assumption here that this is 0. We know water auto-ionizes a little bit, but in these weak acid problems, we assume that we start at 0. If we write our expression for products over reactants, it may not look all that different, but the math is going to reveal something. When you go through x squared is equal to 3.55 times 10 to the minus fifth, again, that's assuming that this is 0. We get a value of x, which is 0.00596. And here, the check of the assumption shows you we have a little bit of a problem. It's not so much a problem, it's just the fact that this x value is almost 12% of the value it's being subtracted from. That means we need to do successive approximations. And just to remind you, what you need to do is to take the value you just solved for, the x, and actually place it in the equilibrium expression and see what we get. So I'm going to do x squared over 0.050 minus the first x and do a calculation to see what the new x is. Obviously, I'm saving a little time here. I did this on my paper previously. And the second value, notice, is a little bit lower than it was before. And I think you know where we're going with this. I say the standard operation is to take this x and go through the process a third time. If you do that, you're going to get a value that's a little bit higher or in the middle of your two assumptions. And that is exactly what we get. Our third x ends up being 0.00561. This ends up being 11.2% of the acid dissociates. So with the concentration of 0.50, we saw that 3.8% of the molecules dissociated. In the more dilute form, 11.2% dissociated. Does that conform with any principles we know? And if you think about it, the answer is yes. It actually has to do with Le Chatelier's principle. If you add water to this equilibrium, because there are essentially two terms in the numerator, or molarity squared, and one term in the denominator, the dilution factor is going to have a greater effect on the right-hand side. I just noticed something here. I forgot to write my anion there. Adding water, essentially, in B, basically diluting the system, drives the reaction to the right. I'll say a la Le Chatelier. Okay, so diluting the protons and the fluoride is going to have a larger effect than just diluting the denominator, the HF. And so since you're making the numerator too small, basically the Q value becomes small, becomes less than K. That drives the reaction to the right. And so we get more dissociation. Let's take a look at another weak acid. This one is a polyprotic acid, and really this is kind of the ultimate version of accounting for all the ionic species. I asked you to use your reading assignment of example 8.2 to look at carbonic acid and take what you learned from that into this problem. So in short, won't write every gory detail, but in short, the dissociation of the first proton is going to follow Ka prime, or Ka1, whatever you want to call it. That value is 7.5 times 10 to the minus 3. This problem asks us to start with a 0.100 molar concentration. And I don't know if the mic is picking up all the glass they seem to be breaking outside my window, but it's kind of funny that someone is throwing a bunch of glass into a dumpster. And in our weak acid problem, we do need to do successive approximations. Turns out that this x value is too small, and my ultimate value is that x is equal to 0.0240 molar after 3 successive approximations. My point in doing this problem for you kind of in a shorthand version is I kind of just want to show you the main structure of the problem without getting into the details. I'm assuming that you could do all of these on your own. But here's the ICE table for the loss of the first proton. Since this is a triprotic acid, you're going to need a different ICE table for the loss of the next proton. Keep an eye on the reaction that you're using, though. The X that you basically went toward in part A becomes the initial concentration in part B. So the initial concentration of the dihydrogen phosphate and the protons fill up spots on the initial line. In the change line, I'll use the letter Y to distinguish it from above, means that we're going to get a different amount of dissociation than we did in the first part. Actually, if you notice here, it's kind of like we have a buffer. Well, we do have a buffer in a sense because we've got, oh, I'm sorry, we don't. No, the protons don't count as the buffer. If you have an acid and its conjugate, then you have a buffer. For this one, though, this is interesting. The Ka2, as I mentioned in class, is always substantially smaller. It's 6.2 times 10 to the minus 8. There's much less dissociation from the anion than there is the parent, which was neutral. In this case, we're going to get y times 0.0240 plus y over 0.0240 minus y is equal to the Ka2. If we make the assumption that y is small here, you could see that the concentration of the hydrogen phosphate is exactly what the Ka2 is. 6.2 times 10 to the minus 8 molar. Okay? And then finally, what do you do for the loss of the third proton? In this case, the hydrogen phosphate dissociates into phosphate anion and another proton, but the ICE table, you have to be careful, is going to include an initial concentration that we just calculated, but the concentration of the protons is mostly coming from the first loss up here, so here we have this value put in. I'm going to use the letter Z to distinguish dissociation. And in this case, Ka triple prime, or Ka3, depending on what your source information is really tiny. It's 4.8 times 10 to the minus 13. That's going to be Z times 0.0240 plus Z over 6.2 times 10 to the minus 8 minus Z. What do we see here? Well, it looks like we could make an assumption again that the plus Z and the minus Z are going to be awful small. And if you do that, our final concentration is practically infinitesimal. I get a value of 1.2 times 10 to the minus 18th. Pulling off that third proton is just really, really a small value when you get all said and done. So I'm going to change my color here and just highlight all the species that are swimming around in an aqueous solution of phosphoric acid. First, you're going to have your concentration of your protons and your H2PO4. Actually, I forgot to do this over here. The parent acid is going to have a concentration that's 0.024. So that's going to be 0.976 molar. That's my concentration, my parent acid. The concentration of the dihydrogen phosphate is here. The concentration of the hydrogen phosphate is right here. And finally, the concentration of the phosphate is way down here. So this is a soup full of lots of different ions at very different concentrations. I hope this helps out your understanding. If you have any questions at all, please drop an email, especially if you find a mistake that I did. I'm going to drop another video for the other two problems in a few minutes. Bye.